Hey everybody, I am tuning into you today to bring you a lesson about rate of change, the nature of change. Stay tuned here. Let me just get going and we will explain to you all about the nature of change and rate of change. So here we go. Just make sure once you're done watching this video about the nature of change that you check into Microsoft Teams to see if there's any additional worksheet that goes along with it. And yeah, make sure you complete that, of course, as well as watching this video to the end. So the nature of change. Today we're going to discuss the idea that Earth is a forever changing environment, that things on Earth just don't seem to stay the same over time. They change, they morph, and things are different. So if we think about what the definition of change is, right in here it says, what is the definition of change? Change is when the properties of matter or the characteristics of matter have been altered. So obviously there's something that's different when a change has occurred. And if we think about predictable versus unpredictable changes which occur on Earth, I want you to kind of think about things with relation to Earth science, something related to Earth science, maybe to this, Earth or space systems that are predictable. Predictable meaning we know that they're going to occur before they actually do, versus things which are unpredictable. So what kind of changes, again, related to maybe that of Earth science, can you think of that are predictable versus unpredictable changes? So let's start with predictable changes. Predictable changes can include things like day and night. Obviously, we know that each day is followed by night and night is followed by day. Even the length of day to night we know is very predictable. Before winter comes, we know that the days are going to go shorter from now until December 21st, which is the shortest amount of daylight hours that you have on any given day. Again, we call this the winter solstice. And after December 21st, the days actually increase of the amount of daylight you get each day by about a minute or two until we get to the summer solstice on June 21st, which is the longest amount of daylight hours that we get on any given day during the year. So day and night are very predictable. Another predictable change on Earth would be seasons. We know that every summer we're followed by the season of fall. Fall's followed by winter, which is followed by spring, and it repeats the pattern again and again. Another two examples of predictable changes here, we got our moon's phases and tides. Tides, if you don't know what tides are, it is basically the highering and lowering, if you will, of water levels in or near the ocean. Okay, so we will see in areas around Long Island, sometimes the water comes up by a couple feet and then it goes down by a couple feet. And again, this is a very predictable thing, which is actually caused by the gravitational pull of both sun and moon on the Earth. Another two things which are examples of predictable changes related to Earth science would be a planet's period of rotation. We know that planets spin once on their axis in a very predictable time, period of time. Again, we call that the period of rotation versus planet's period of revolution. Each of the 8 planets which belong to our solar system take a certain amount of time to orbit once around the sun. Okay, again, these are all examples of predictable changes. So let's jump over to unpredictable changes. And I often like to think of unpredictable changes as something like almost like a natural disaster. So things like earthquakes, volcanic eruptions, wildfires, avalanches, and many weather events, not all, but many weather events are very unpredictable. So you think about unpredictable things, we're thinking about things that exist or happen that we really had no idea that were going to occur, how or when they did. So again, unpredictable, no idea, right? So changes on Earth are both predictable and unpredictable. And again, a change is just when properties of matter have been altered in some way. So next slide. When it comes to change, okay, a very good way to show change over time are these things which we call line graphs, right? And there are 4 basic line graphs that you are going to be using throughout the entire year this year. So in essence, this lesson is actually quite important because when we think about this lesson, the concept of these line graphs carry through basically to every lesson every unit that we teach throughout the entire year, like I said. So you definitely want to make sure that when I'm done with doing this slide and this slide, that you have a good understanding how the relationship, how each graph works, and also, of course, what the name of each graph is. So let us begin. I'm going to get my writing tools up here. Let us begin with the first graph on the left, which is known as your direct relationship graph. And a direct relationship, sometimes they're also called positive relationship graphs, is basically when both, okay, let me just exit out here for a second and get my little drawing tools up, but it's when both things, okay, your X and Y axis basically relate to each other in a positive way, that if one variable increases, so does the other. So let me show you what I'm talking about. Here on the X axis, you have variable 1. And then if we go up to the Y-axis here, you have variable 2. Oh, that was a terribly drawn circle. Let's see if we can redraw that just a little bit nicer for you guys. We're going to go up to the eraser here for a second and just erase that. And let's see if I could draw this just a little bit neater for you guys. So yeah, variable 2. That's not much better, but you know what I'm getting at here. So variable 1, variable 2. A variable is anything that you're plotting data for on a graph. So say I was plotting height with age, and on the bottom here, this is basically your age over 12 years. So it goes from birth at 0 here, and your age is increasing as you go across the x-axis. So again, if I label this variable as age, and then I had this variable as height, right? And I don't know anybody who's actually 12 foot tall, or even anybody who's 9 foot tall, but if this variable was height in feet, okay, this person is a giant, but understand that as you increase your age from 0 to say 10 or 12, this graph shows a positive relationship that each year that you lived on this planet, your height continued to increase. So again, this is referred to as a direct relationship where both variables increase. I got to get better with writing with this marker here. This is terrible. But again, a direct relationship is simply where both variables increase with one another. Okay, direct. Understand, you need to know that with association with this type of graph. Again, line goes up as you go to the right, because both variables increase with one another. That brings us to the indirect, or sometimes it's called an inverse. Okay, so this one was the direct, understand that, versus this one is your indirect. And an indirect or an inverse relationship, sometimes again called the negative relationship, it says it here, and then again, this is your inverse relationship. An inverse or a negative relationship is one where the line actually decreases as you go to the right. And what this is showing is a relationship where one variable increases, whereas the other variable that they're plotting is decreasing with that increase. So imagine this is, time in somebody's life, right? And it is a proven fact that once people hit 40, yeah, like me, once you hit 40, that your ability to hear actually decreases slightly each year, basically for the rest of your life. So if you were graphing, say, somebody's age increasing with their ability to hear after 40 years old, so like say this was actually not, instead of a 0, this was 40, and this was like 42, and this was 44, and 46, and continuing on, right? As you get past that certain threshold in life, your ability to hear actually gets worse even though your age is going up. So again, this is what we call where the line goes down across the graph as you go to the right. An inverse, okay, the word inverse is right up here. I believe I covered it up a little bit right in here. You got your inverse relationship, or we also call this a indirect relationship, okay? So note the difference. Positive or direct relationship, the line goes up and to the right, whereas an indirect, the line goes down and to the right. And again, on the first graph, both variables increase, whereas on the second graph, one variable increases as the other variable being plotted decreases. Okay, so you should definitely know the difference. I want to say a solid like 80 to 90% of graphs in earth science, probably closer to 90%, are plotting either the direct or indirect relationship. Which brings us to our other two relationships, which is our constant graph versus our cyclic graph. So a constant graph would be this one here, versus a cyclic graph would be representational of the one on the right. And a constant graph is simply where you are plotting something that doesn't change over time. So say that you are driving your car and you're on your way down to Florida and you're on basically cruise control, and you set your cruise control for 55 miles per hour, right? And your velocity of your car is going again 55 miles per hour. And your velocity is on, again, cruise control for a good hour. You have hit no traffic, you're not slowing down, you're not speeding up. And again, for the 1 hour that you are traveling on that highway, your speed or velocity is maintained exactly at 55. If I plotted that on a graph, you would actually see a straight line as you see here. Again, what this is showing you, sometimes they call it a static or a constant graph. What is it showing you? It's showing you no change over time, and that's why the line doesn't change. Versus a cyclic graph is actually a repeated change over time. And I particularly chose this graph on purpose because this shows you a phenomenon which we're going to discuss next about something called sunspots. And sunspots are kind of like these dark freckles on the surface of the sun that show up in a very cyclic pattern. So every 10 to 11 years, we find that all these spots show up on the sun, and then they start to decrease, 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 and exactly 10 to 11 years after the last peak, you get another peak of sunspots. And if we plot this phenomena over time, you can see a very cyclic up and down pattern, if you will, that repeats itself. So again, basically from every top to the next peak on this graph, you will find that it's about 10 or 11 years. Again, we measure from here to the next peak on the graph, a very cyclic kind of pattern where we peak out with about, a whole bunch of sunspots again and about 11 years later. So again, cyclic is a repeating pattern which is shown on a graph over time. So there are your four relationships, and that is something that you can't kind of mess around with in earth science. You totally need to know these relationships. You need to know the names of the graphs and exactly how they work. Which brings us to the last part of our lesson, which is something called the rate of change. So there is a formula which we use in earth science that actually helps us figure out the speed or the rate at which things change over time. And if you look at your cover of your earth science reference tables, note down here, I put earth science reference tables page 1. I actually gave you the equations box. We've actually talked about this box when we talked about density. But the formula one above density is the rate of change formula. And if you note, this rate of change formula says it's the change in value divided by time, right? Well, let's get this formula to work. Let's figure out how this formula works. So if I go to my next slide, right, and I think about that formula, rate of change is change in value over time. And I give you some data, right? Let's get to this next one. And I give you some data. And this data is actually showing a direct relationship, right? We just discussed that. But what this data is showing you is that carbon dioxide concentrations have been steadily increasing with this direct relationship over time. So if you look at the x-axis down here, let's get my marker back up again, right? If we look at the x-axis down here, this is basically years. And if I look at my y-axis, which is this axis in here, I'll put y there, it shows you the concentration in parts per million of carbon dioxide in our atmosphere. And a very appropriate and a very ninth grade level rate of change question might ask you something like this. They may say, how many parts per million has the carbon dioxide changed? So how many parts per million has carbon dioxide changed between the years of 1980 and 2020? So they're looking to see if you can plug this type of question with this data into a rate of change question. So again, rate of change is the change in values, right? This change in field value divided by time. So if we look at the values are the parts per million of carbon dioxide, which has changed between the years of 1980 and 2020. So I'm going to need to use my graph to get some data. And again, it's the change in value divided by the time. So if I set up a little divided line and I think about my time, the time was from 1980 to 2020. And time is always going to go on the bottom part of your equation, right down here. So from 1980 to 2020, I could even use my graph to kind of look at this, but I am going 40 years. So from 1980 to 2000 is 20 years, right? And from 2000 to 2020, which is the last part of this graph, they didn't even label it 2020 right now, right? That's a 40-year difference. So again, 40 years would be on my bottom of my division problem. And then the top of my division problem is I got to find the differences in the parts per million of carbon dioxide for the starting and ending years. So my first year was 1980. My end year is going to be 2020. So I'm going to go up. I'm going to stop when I basically get to my graph. If I go out to the left here, I got 340 parts per million. Okay, and then I'm going to go to the year 2020, which is going to be this end of this graph, basically. That's now. And I'm going to go up, right? And what I'm going to do from here, it's basically ending right about in here. I'm going to round up a little bit here just to get a nice number for you to learn this with. We got about 400 parts per million. So to find my change in value, what I'm doing is I'm taking both of the parts per million, the count of carbon dioxide for the 1980 and the carbon dioxide for the 2020 year now, and we find change mathematically by subtracting. So if I do 400 minus 340, okay, that would give me a difference of 60, right? 400 minus 340, so it's 60 parts per million of carbon dioxide divided over a total of 40 years. And again, I'm going to need to use a calculator to do this. So if I pull out a calculator, or if you don't have a calculator available, you go to your phone. You might want to pause this video for a moment. But again, I'm going to put into my calculator 60 divided by 40 years. And I'm going to tell you right now that my difference is 1.5 parts per million. And that's going to be per year. And again, what this is breaking this down is it's telling me each year between 1980 and 2020 that carbon dioxide has increased, obviously it's going up, by about 1.5 parts per million per year. And that's exactly how you do rate of change. You take your two values, you subtract them, you find the difference, and then you simply divide that difference by the amount of time that it took for that difference to occur. So hopefully this lesson is, fairly easy for you. You will find an attached worksheet in Microsoft Teams that is more practice for you on this formula particularly, because this formula, of course, when it comes to math, repeated, like kind of practice on it makes you a master. So please make sure that you go back to your Teams assignment. You click on that worksheet, complete that worksheet. When you are done, you are to submit it in your Microsoft Teams assignment tab. Please don't just submit back a blank worksheet. You don't get credit for that. And as soon as I see it come in, you'll get credit for that. And by the time we're done practicing that, we will have a lab either tomorrow or the day after. And that's that. So I hope this lesson was easy for you. I will certainly touch base with you, and have a great day.